All right, let's solve this system. So the very first thing we do is we write down our system of equations that we want to solve, which is 3 minus lambda v1 plus v2 equals 0, and v1 plus 3 minus lambda v2 equals 0. Now, we could use our shortcut here. The trace of A is 6, and the determinant of A is 9 minus 1, which is 8. So therefore, our differential equation, it's the characteristic equation, is given by the following polynomial. Good. And then we try to factor that if possible. Maybe a 2 and a 4, huh? Good. And then for each of those numbers, we plug them back into our system. So then we have 3 minus 2 v1 plus v2 equals 0. Remember, you don't have to have the other equation if you don't want. You can, sometimes it's handy to have it just to check to see if you do indeed have the same equation. So in this case, we have v1 plus v2 equals 0 twice, right? Good. So therefore, the vector we pick is 1 minus 1. Now we do the same thing for lambda equals 4. 3 minus 4, v1 plus v2 equals 0. So that gives me minus v1 plus v2 equals 0. And so in this case, I can choose 1, 1. Good. And now we write down our solution from that. E to the 2t 1 minus 1 plus c2e to the minus positive 4t times 1, 1. Good, and we're done. That took 2 minutes. Excellent. All right. So now we're going to take a look and see what happens with complex eigenvalues. Okay, so that comes from the characteristic equation. And maybe we just go ahead and try one just to see what happens. Let me pause for a second and I'll write down the problem that we'll try to solve. All right, so we'll try x prime equals 3 minus 2, 1, 1 times x. So the first thing we do is we get our trace, our determinant. Trace is 4. Determinant is 3 minus 2, which is 5. And so our characteristic equation is lambda squared minus 4 lambda plus 5 equals 0. And then if we try to solve this, let's see, I already know it's going to be complex, so let's go ahead and complete the square. Oops. Minus 4 lambda plus 4, and then we have another plus 1. I'll bring over to the other side as a minus 1, and this is where my perfect square comes in, right? So I see that lambda is going to be 2 plus or minus I. Good. Now, for lambda equals 2 plus I always use the positive. You don't. We could do the same thing for 2 minus I, but we really only need 1. We'll have our 3 minus lambda v1 plus, minus 2 v2 equals 0, and then we'll have our 1, I'll just be 1 plus 1 minus lambda v2, plug in 2 plus I, and what do we get? We'll write it down here, 3 minus 2 plus I times v1 minus 2v2 equals 0. Now I should say that in the notes I go through the second equation, and it doesn't look like the two equations are multiples of each other, but if you allow complex constants, they actually are. And so we're only going to need the first equation here like before. And so simplifying that, it looks like 3 minus 2 is 1 minus I v1 minus 2v2 equals 0. And so I can just set my eigenvector to be 2 and 1 minus I. Good. All right. Now, if I were to plug in my the complex conjugate for lambda, I would actually get the complex conjugate for v. Instead, we're going to use a trick that we did in chapter 3. And we said in chapter 3 that if r is complex, right, then we just took one r, and we just took alpha plus beta I, right? And so then going back to the ansatz would be e to the RT. And so the full solution then in chapter 3 was C1 times the real part of e to the RT. And we added that to the imaginary part of e to the RT. Well, actually the same thing is going to happen now. With lambda equals 2 plus I and vector v being 2, 1 minus I, we're going to compute the same thing. Our x of t is going to be C1 times the real part of e to the lambda t times v plus C2 times the imaginary part of e to the lambda t times v. Okay, so we just have to compute what e to the lambda t times v is. And so those lambda and v are complex now, so e to the lambda t times v is e to the 2 plus I t times 2, 1 minus I. Okay, so that's e to the 2t times e to the it. So I'm going to pull out the e to the 2t. 2, 1 minus I. And that's e to the 2t times cosine t plus I sine t. Right. Times 2 and 1 minus I. Good. So let me go back here. That's e to the 2t times 2 cosine t plus I 2 sine t. And then when I multiply this times this, right, I'm going to get, for the real part, I'll have cosine of t minus I squared. So cosine of t minus I squared is plus, so that's sine plus sine of t plus I times, let's see, that'll be minus cosine. And then where's the other imaginary part coming from? 1 times sine is going to be plus sine. Okay, and so we see here that the real part of e to the lambda t times v is e to the 2t times 2 cosine t and then cosine of t plus sine of t. And then the imaginary part is going to be running out of space. Oops. E to the 2t times 2 sine t minus cosine of t plus sine t. Good. And then for the full solution, then I add C1 times that plus C2 times that. Good. So x of t equals C1. In fact, you could pull that e to the 2t all the way out, right? C1 times 2 cosine of t cosine t plus sine t. The one thing I just wanted to really focus on, really emphasize, is that there is no imaginary numbers in the solution, right? That's all real. Good. There is our solution right there. Good. So again, we'll summarize here. Let me pause and I'll write down the summary and we'll go through it briefly. Okay, so here's the conclusion page so far. If we're trying to solve x prime equals abc dx, I like to write down the trace and the determinant, so we'll just go ahead and fill those in. Trace is a plus d, determinant is ad minus bc. Remember that the ansatz is e to the lambda t times v, where we have this system of equations that is the primary thing that we need to solve. So in order to solve that, we need to solve the characteristic equation for lambda, and that is a quadratic formula. And so we know that there's three different types of outcomes depending on if lambda has distinct real solution, or if lambda has distinct real solutions, if lambda is complex, or if there's just a single root. And so the two cases we covered in this video were that, or in the last two, is that if lambda has distinct real values, then we can write down our solution as a linear combination of the two ansatz, if you will, just like chapter 3. And just like chapter 3, if lambda is complex, then our solution overall, we want to take the real part of our ansatz and the imaginary part of our ansatz as our the two pieces for the fundamental set of solutions. And that's it. So in the complex part, the real headache maybe, or the hardest part, is probably just computing the e to the lambda t times v, just remembering how to compute that. But once you're through that, yeah, no problem. Okay, well, I'll stop there. And let's see, I think we'll go through the third case next time. All right, see you later.